let us now look at an example of a function which is a linear transformation. So our function t, so this time we'll go from R3 to R2. I'm not looking at examples of linear transformations between R7 and R9, just because there will be too many variables involved and that will just take too much space. Okay, and if you understand what happens for linear transformations between R2, R3, R4, then it should mean that you can understand what happens in general. So, all right, so t will be given by the following formula. So t applied to a vector x, y, z in R3 will be the following vector in R2. So let's say it's 2y minus 7z for the first component. The second component will be square root of 5 times x. Right, so if we look at this, now that we have our addition of numbers and scalar multiplication of these variables by some constant in front, right? So the function f of x equals square root of x is not linear, but it's not what we have here. Here we just have the scalar square root of 5 times x. Okay, so if I add here a square root of x or square root of absolute value of x or something like this, then this would not be linear. But the square root is just on the 5, not on the x. Okay, so it's not going to cause any problem. So I'm claiming that here t is a linear transformation. All right, so I want to prove this using the first axiomatic definition. So again, we need to check two conditions. So we want to check first that t of u plus v equals t of u plus t of v, right, for all vectors u and v in R3. Okay, so I'll write these vectors explicitly. Since I have two, I'll use as coordinates, I'll use x1, y1, z1 for u, and x2, y2, z2 for v. So, all right, so let's start with this. So we look at t applied to a sum of two vectors, x1, y1, z1, plus, so this is my u, my v will be x2, y2, z2. Right, so I want to prove, so I need to work with general vectors, so I cannot just give x1, y1, and z1 some specific values. Right, I should not just check this for two specific vectors, u and v. I have to check just for any vector, so I have to keep using these variables. Right, so I want to apply t to this sum. So here I have to compute the sum first before I apply t. Right, well, the sum will be the vector with components x1 plus x2, y1 plus y2, z1 plus z2. Okay, and now I can apply t. So I use this formula. So what is y? Well, y is y1 plus y2. So I'll get 2 times y1 plus y2. Okay, and then minus 7 z, but the z here is z1 plus z2, so I just put z1 plus z2. Okay. And then the second component is square root of 5. Okay, and times x, which is x1 plus x2. All right, so, okay, so I got this. I need to compare it with t applied to this sum. Okay, so, all right, so let's compute this. So what is t applied to x1, y1, z1, t applied to this vector, plus t applied to this vector. right? Well, I just use this formula, but I've got, I put indices 1 and 2. Okay, so you just get 2y1 minus 7z1, and then square root of 5 times x1. Okay, same thing with the other vector, except that I get a y2, a z2, and an x2. Okay, now I can sum these two. Right, so if I sum these two, well, we just add components. The first components become the sum of this plus that. So I can write it as 2y1 plus, right, I can sum these two, 2y1 plus 2y2 minus 7z1 minus 7z2. Okay, and the second component is just square root of 5 times x1 plus square root of 5 times x2. Okay, now I have to, right, so you want to check that, right, you need to check that this is equal to this, right? So, I mean, the left-hand side is this sum, the right-hand side is this one. Okay, so it means we need to check that this is equal to that. Okay, and this can be checked directly. Now we're just using properties of numbers, right? 2y1 plus 2y2, this is 2 times y1 plus y2. Okay, same thing with negative 7 times z1 plus z2. It's negative 7z1 minus 7z2. Okay, and the second component equals this one. So now we can say that, yeah, these two are equal. Okay, so this is true, so then it means that, yeah, we have this equality here is satisfied. So this equality here implies that, yeah, here we do have an equality indeed for any vectors u and v in R3. Okay, so this is the first thing to check to see that T is a linear transformation. There's the second axiom that needs to be checked, so which is what I'm going to do right now. So to complete the proof that this function T is a linear transformation, we should check the second axiom, which says that if we apply T to any scalar C times some vector V, then you get the same thing as when you first apply T to V and then multiply with a scalar C. All right, so so we need to compare both sides. So right, so I need to see what happens when I apply T to C times some vector V, which is an R3, so I will write V as x, y, z. All right, so here I first need to do scalar multiplication before I can apply T. So I'll get the vector Cx, Cy, Cz. Okay, and then I apply T, which is given by this formula. Okay, and all I need to do is to replace x, y, and z by d. So I put the C in there. So 2cy minus 7cz, and then square root of 5 times cx. All right. And now I'll have to compare here with c times t of v. So what is c times t of v? I still have the t. C, t, v is x, y, z. Okay, so I get c. Now I apply t first, so I get this. I get c times 2y minus 7z, and then square root of 5 times x. Okay, and it's just vector times the scalar, so I can put the scalar in front. So if I put the scalar in front, I'll be multiplying both components by c, so I'll get the 2cy minus 7cz, right? I can put the c, I multiply this number with c, I can distribute the c inside, and here I'll get square root of 5 times cx. I mean, c times square root of 5 times x is equal to this. Okay, so, right, so in this case, right, so wanted to check if is this equal to this, right? The left hand side is this, the right hand side is this. So are these two equal is the same question as are these two equal? Well, if you go here, you can see that this is equal to this vector, which is really equal to this one, which is equal to that one. Okay, so it means that yes, this is indeed an equality. Okay, so these two axioms are satisfied, and this implies that T is a linear transformation.